around from that. Although if you want that, then I'll take one side of it. I just have to write down which side I want. So what this says is that those data points that are off the line are very strongly, even in the marginalized model, where I've marginalized over all possible values for p bad, y bad, and v bad, even marginalizing over it, those data points got large probabilities of being outliers, even in the marginalized chain. By the way, I labeled every data point that has a probability greater than 1/2 of being off the line. So those 3 data points are the only data points that are in fact judged to be off the line by the method. 5 of the data points were actually generated as outliers. So 2 of the points we generated as outliers happen to hit the line. And that's one of the things that tells you that the Bayesian answer is not necessarily the truth, it's just the best thing that the model does with the data. And this model is very made up. This is a very contrived model. I invented this bad outlier probability distribution. So my message is not, the message I'm trying to say is not model the outliers with a Gaussian. That is not my message. My message is model the outliers. That's my message. My message is if you have outliers, don't try and cut them out or throw them away. Model them. You don't know very much about them, but you should model them. And the reason you should model them is it's only by modeling them that you can potentially marginalize them out and learn what the answer is in the face of them. Because in the face of it, this model that we started with is dead wrong. Like this model up there with the 1, 2, 3, 4 assumptions. One of those assumptions, or many of them, have to be wrong. Yes?
So your suspicion is if you had modeled p bad as a uniform distribution across the entire plot with some normalization, your answer in the sense of slopes and lines, it would be very similar?
Well, p bad, the capital P bad I'm using here is just an amplitude, overall amplitude.
The little p bad. If that was a
just a uniform block.
Square, yeah.
Right, so one option I could have used for the bad probability is that they just can come from anywhere inside the square. And yes, that would have given very similar results. The fact is actually, because there's only 3 outliers, it doesn't really matter how we model them. We always get the same 3 outliers. So the outliers are not taking a lot of the information in this problem. If I made 80% of the objects outliers, that would be a different story. Yes?
We've just said this. There's only one way to do it. But you have a second way to do it. So there's no science either.
Good. So what's the difference between choosing a linear regression methodology out of a book written in 1960 versus writing down a generative model that has ad hoc things? So you either choose an ad hoc method or you choose an ad hoc model. Okay? So there's 2 important things. One is, when you choose the ad hoc model, you're at least controlling explicitly all of your assumptions. And it's trivial to change those assumptions and see how they change your answer. It's very straightforward to replace this p-bad model with something else, with a top hat or something else. I can control this assumption. So that's the first thing. The second thing is that any model you pull out of a book from the 60s was optimized or generated for data with some particular assumptions or beliefs about what is robust and not robust about the data, which in general will be different from what's robust and not robust about the data you yourself have. So even though this model is fundamentally made up, it still accords with some kind of ideas about what's going on with this data set. There's no, my point is there's no one-size-fits-all. You can't just take some model and hope it'll work on some method and hope it'll work on your data. You have to look at your data and use it to inspire your model. In principle, you can make this bad probability some very complicated function that models all sorts of details about the bad data. But with only 3 data points, it's clearly not necessary. But you want that flexibility as your data set grows. Does that?
Yeah.
Okay.
It was also a semantic argument as to you saying
Good.
it's a procedure, so it's not science. To some extent, it's the same.
I agree that whenever you're for exactly this reason, you in any situation in astronomy that I know about, you want to write down some assumptions under which your work will be correct. That's a good thing to do. But in every case I know about, those assumptions are violated. Then you have to deal with it. The question is, do you deal with that before you even start by saying, forget all the data were generated, I'll just take this method that's written down in this textbook? Or do you write explicitly what you're assuming about the violation of the model and allow your colleagues to evaluate that? So I still think this is more science. Yes?
If the objection is that writing down a model of the data and the outliers isn't science or is somehow not scientific, what is science then? Isn't science making models for stuff?
Let that stand. I agree with that. By the way, here is the plot that some of you achieved last night. But this is now, in this 5-dimensional model, now marginalized. So this is the 2D M versus B distribution. And how did I marginalize this? Trivially, I just plotted my samples, because the MCMC sampling is a fair sample of the distribution. So if I plot any 2 parameters, what I get in the plot is the marginalized 2D distribution. There it is. And you can see there, if you look very carefully at it, you might see some hints of bimodality. This is not a Gaussian. In the pure linear least squares case, this case, the posterior distribution function is exactly a Gaussian because it's a linear operation on a quadratic model. So you get quadratic outputs, which when you take the e to them, they are Gaussian. So the posterior for the pure linear least squares is in fact Gaussian. This one, if you're very good at it, as you can see, this is not a Gaussian, and I'll show you that in more detail right now. Here are those same data points, the data points we started with. Now I divided all the error bars by 3. Okay? All I did was take all the error bars, divide them by 3. I'm going to run exactly the same model. Anybody have any predictions? More outliers. That's a good prediction. More of these data points are going to get counted as outliers, right? Because the error bars just got smaller, so the probability that those known errors are correct and the errors are Gaussian and all that, that's just going to go, right? Something's going to go wrong there, so there'll be more outliers. Anybody want to make any other predictions? Bill, you want to make a prediction?
Bimodal.
Okay, let's check. Here's my sampling for my posterior distribution function. Looks suspicious. Well, one interesting thing is even when I took all the error bars down by a factor of 3, the fit still basically got the right answer. Which is amazing because a large fraction of these have a probability greater than a half of being an outlier. Now, by the way, the correct bet on that point is 10 to the 146 euros. That's a big bet. In fact, the entire world can't even make a tiny fraction of that bet against my euro. But notice, very large fraction of the points got a probability greater than 1. Even that 0.7 is a probability greater than 1. That's 10 to the 0.7 is the probability ratio bad to good. So it's like a, whatever, 5 to 1 or 6 to 1 probability of being bad. So all of those points got marked as probable outliers. And now let's look at the M and B distribution. Bill, you're right. Not just bimodal, multimodal. The M and B distribution went to hell. And that's kind of a suggestion that maybe the model was really very wrong. And the model is very wrong because, in fact, the error bars were wrong by a factor of 3, which means the error variances were wrong by a factor of 9. Yes?
So each of these islands corresponds to different choices of declaring things as outliers and fitting to the rest, so to speak?
Exactly. In fact, each of these lines is a choice. Did one of these things work? So each of these lines is a choice of which